Okay, thank you very much. So, okay, so this was all about the muon. So let's now start our lesson. So there was a question at the end of the last lesson that I can summarize here somehow. So how do we deal with the ambiguity in the assignment of the Clebsch-Gordan coefficient in same isospin two-particle systems? I think this was the question. So I admit I couldn't find a clear answer in textbooks, okay? But I worked out a few relevant examples, and I think I can extract from them some convincing answer to this. So let me go. Let me go through these few slides. So one first case is the first one. So suppose you have a system of two isospin 1/2 particles, for instance, a proton and neutron system. Okay. Then, if you take the proton as the first particle and the neutron as a second particle, the third component of isospin is plus 1/2 for the proton and minus 1/2 for the neutron. Okay, and then these are essentially the square of the two Clebsch-Gordan coefficients. Now, what about if you swap the order? Suppose now we take the neutron as the first particle and the proton as a second particle, because there is in principle no reason to choose one or the other, right? So in this case, the negative third component is here, minus 1/2, the one for the neutron, and the positive is there. But the problem is that you get a different sign here on the Clebsch-Gordan coefficient. Now, a similar problem we have, for instance, for 1 times 1 system. So, for instance, pi plus into pi minus, pi plus pi minus systems. Okay. Again, we have a situation where when you swap the order of the two, you get a different sign in one of the Clebsch-Gordan coefficients. Okay, and this problem, I mean, you can generalize for any same isospin two-particle systems. Okay, so I just pick up two examples here. Whereas if you take a system with different isospin, there is no ambiguity at all. Okay, there is no problem in this case. So the problem is only when you have two same isospin systems. So let me go a bit into the details. So once you decide the order of the two particles, of course, you are fixing your spin isospin state. So for instance, the state 1 plus 1, 1 minus 1 is a different quantum state than 1 minus 1, 1 plus 1, okay? And of course, if you have different quantum state, you also should expect to get a different projection in the combined basis, so in the other basis. Now, in particular, if we interchange the order of I1 with I2, okay, so in other words, if we exchange the order of the two particles, the combined state, so the one in the new basis, may change sign according to this general phase relation for Clebsch-Gordan coefficients. So this is the Clebsch-Gordan coefficient for I2, I1. This is the one for I1, I2, so the two are switched. And the two are related by a sign, either a plus or minus sign, which come from this coefficient here. Okay, so this depends on the value of I1, I2, and the total I. Now, however, this does not affect the cross-section or the decay width calculation. That I think was the worry about the question that was raised last time. So let me show you some examples. So the first example is a proton-neon elastic scattering. Okay, proton-neon into proton-neon. So the third component in the initial final state is 0. The total isospin in the initial final state can be 0 or 1. So this is the Clebsch-Gordan table that we need. Okay, so we can first of all consider the proton neutron in this order. Okay, so we can define the initial and the final state by taking these two positive Clebsch-Gordan coefficients. So square root of 1/2 1 0 plus square root of 1/2 0 0. Of course, we can do the same with a swapped system. So let's now consider neutron and proton. Let me call these I prime and F prime. Okay. And the difference is that now we have this minus sign here, okay? So the state in the combined basis will get a minus sign in front of the 0, 0 isospin state, okay? So let's now check, okay, the consistency of these two signs, okay? So let me remind you that the coefficient we have to calculate is this one from the previous general phase relation, okay? So for the 1, 0 case, we have 1/2 for I1 plus 1/2 for I2, and then we have 1 because it's 0. So overall, the exponent is 0, so we have a plus sign. So there is no sign change. And in fact, for the 1, 0, if you look, there is no sign. They are both positive. There is no sign change. On the other hand, if we now consider the 0, 0, okay, then one have 1/2 plus 1/2 minus 0. So it is minus 1 to 1. This is minus 1. And in fact, this is why we observe here a minus sign change, okay, between the two. Now, indeed, this quantum state here and this quantum state there are indeed different, okay, of course. But let's now see how these, or if these affect the cross-section calculation, okay? So let's start to calculate the cross-section for the case proton-neutron into proton-neutron, okay? So this is proportional, as we know, to the squared matrix element with initial and final state. We just substitute these two states here. We consider only the diagonal terms, so the isospin conserving terms. The other, of course, cancel out. And this is the results for our cross-section prediction. Let's now do the same where both the initial and final state are swapped. So neutral proton into neutral proton in this case. So in this case, we have to use the I prime and F prime state for initial and final state, okay? And nothing changes because when you calculate this object here, that is the one with the affected by the minus sign, essentially you are multiplying twice the minus sign, okay? One for this, one for that. So overall, you get a plus sign, and so the cross-section remain unaffected. Now, of course, one wants to see what happens if one takes a mixed choice. So suppose now we take the inverse order in the initial state and the right order in the final state. Then, of course, the problem arises, because then you should have you got to have a minus sign here, which will reflect in the final cross-section, okay? And the same if you take the opposite, so proton-neutron into neutron-proton, okay? So essentially, the point here is that if you take the same order or the same prescription for both the initial and the final state, so either this one or that one, you get the correct answer. If you take the different choices for the initial and final state, then you get the wrong answer. Let me go through other examples just to try to convince yourself. Now we take these pi plus, pi minus scattering, okay? So the total I3 is 0, and the total initial and final state isospin is either 0, 1, and 2. So this is the table that we need, and we can repeat our exercise. So these are the initial and final state in the order pi plus, pi minus, and we get the combination of 3 states with the all positive Clebsch-Gordon coefficients, okay? But we can do, of course, the other way around, so pi minus, pi plus. In this case, we have a minus sign here, okay, which is reflected here in our state. Again, let's check the sign of this. So for the 2, 0 state, so this guy here, okay, the exponential is 0, so we don't indeed observe a sign change. For the 1, 0, we get a minus sign here from this coefficient, so indeed we do observe a minus change, sign change. And finally, for 0, 0, it is again an even number, so it is again +1, and we don't see any change. So let's calculate again the cross-section. So again, let's take, first of all, the same order for the initial and final state. So both direct or both inverted, okay? And as you can see, nothing changes. So you get the correct answer in both cases, because the minus sign cancels in between here, because you take it twice. Again, if you take instead a mixed choice, okay, so a different choice in the order for the initial and final state, you get a minus sign here, and so you get a wrong answer for your cross-section prediction. What about now other processes, such as a reaction, for instance? So this reaction we already discussed in lesson 11, okay? So you find in your notes. So the total isospin third component is 0 for the initial and final state, and then we have 0, 1 for the initial state and 1 for the final state, if you remember. So this is again our table, and again we can write down our states in the way we already showed before for the proton-neutron or neutron-proton case. The final state in this case has one fixed isospin, so it's just 1, 0. Okay. So we can calculate the cross-section in the usual way. Now, this is a non-diagonal term, okay? So this goes out, and this is, at the end, our prediction for the cross-section. What if we swap now neutron and proton, so again, the order. So now we have to use I prime as an initial state, but again, the state that changes sign cancel due to isospin conservation, because it is a non-isospin conserving term. So again, the answer is correct, okay? So in this case, it is isospin conservation that removes the sign ambiguity. And the last example I want to show you is now a decay. So suppose now we study the decay of a phi meson into a K plus K minus. So the phi meson is an S bar meson. So S is a strange quark, it's a strange anti-quark. And the 2K plus K minus we studied last time, if you remember. These are the K mesons, so US bar and U bar S. And this is a strong decay, okay? So these are the isospin assignments. The initial state is a pure 0-0 state because there is no up quark, there is no down quark, so it is an isospin singlet state, okay? So 0-0, there is only one possible choice. For the final state, we have our usual two possibilities, okay, depending on the order you take, K plus K minus or K minus K plus. And now you want to compute the decay width, okay? It is as usual proportional to the square matrix element. In this case, so we have this, the sign change is in the 0-0, okay? But the term that cancels now is the other one, okay? That's why I want to put this example here. So now the one that cancels because of isospin non-conservation is 1000, okay? So indeed this one survives and this is the result. If we now swap again, oh sorry, I didn't swap here, but again, K minus K plus, you now use the F prime state, so you now have the minus sign here, and now the minus sign survives, okay? But due to isospin conservation, again, this term here is killed, okay? And when you take the square, this minus sign disappears. So you get the correct answer in both cases. So again, also in this example, isospin conservation removes the sign ambiguity. If isospin were not conserved, these two terms were surviving, and you would have got A plus B rather than A minus B. And so you would have got a difference, which is not the case because of isospin conservation. So I think we can summarize the answer to this question in three different scenarios. So for elastic scattering, the prescription to avoid the sign ambiguity in evaluating cross-section of elastic scattering processes involving same isospin to particle system is to use the same order of particles for both the initial and the final state. So either first put the positive I3 and then the negative, or vice versa, but consistently for the initial and the final state. And then you get the right answer. For reactions or decay, it is isospin conservation in the strong process that ensures the correct and ambiguous results. And for the system of particles with different isospins, so 1, 1/2, 2, 1, etc., then there is no ambiguity at all. Okay. And then you can check yourself that all the results of the previous lessons, all the examples and the problem that we did last lesson are indeed correct. Okay. Any questions?
No, thank you. That's very clear.
Okay, very good. All right. So apart from that, let's now move on to today's lesson. So we already introduced the baryonic number for a state, and it is defined as the number of baryons minus the number of antibaryons. Okay, this is a definition that we already provided before. Of course, we can now be more specific, and we can give this definition now at the quark level. Okay, so at the quark level is 1/3 for a baryon is 1/3, and then the number of quarks minus the number of antiquarks. Now, assigning by convention the baryonic number 1/3 to the quark and minus 1/3 to the antiquark, then of course one obtain, due to this relation here, that the baryonic number of a baryon is +1, the baryonic number of an antibaryon is -1, and the baryonic number of mesons and antimesons are 0. Okay, because you have a quark and antiquark contribution cancel, being of opposite sign. Now, it is important to stress again that all known interactions conserve the baryonic number, okay? And the best experimental limit comes from the search of the proton decay, okay? So we assume today that the proton is a stable particle, okay? But we are not 100% sure, okay? It's possible that the proton might also decay in lighter particles. So the lower limit on the lifetime of the proton measured through the baryonic number violating decay of the proton into a positron π0 is of the order of 10 to the 34 years. 10 to the 34 years. Okay. So again, this is a baryonic number violating decay because we have a baryon in the initial state and the meson and an electron in the final state. So the baryonic number would not be conserved in this process. But if you do observe this kind of decay, which is not observed yet, okay, then you found something new, something that is beyond standard model, because standard model predict that the baryonic number must be conserved in the decay. Okay. Now, the lower limit on this on the lifetime of the proton is 10 to the 34 years, which is an extremely long time. It is actually 24 orders of magnitude larger than the age of the universe itself, which is 14 billion years, more or less. So to reach such level of sensitivity, one needs to control 10 to the 34 protons for several years, and to be ready to detect the decay of a single one in case it would happen. Okay. So these searches are for ultra rare events, have to be carried out in a virtually background-free environment, of course. And for the proton decay search, the main source of background comes from cosmic rays. So the best way to search for proton decay events is to shield cosmic rays, and so to work in deep underground laboratories. So the Super Kamiokande detector in Japan, which is dedicated to the study of the neutrino oscillation phenomenon that we will study next in the course, contains something like 22,000 tons of ultra-pure water, okay? And so water is, of course, contains protons, and so this corresponds to 7.5 10 to the 33 protons in this volume of water, okay? So we are essentially of the order 10 to the 34, indeed, protons. So this is an ideal place to look for the proton decay, for possible proton decay events. So this is a huge tank, and all the surfaces of this tank are so this is completely filled with ultra pure water, and all the surfaces are covered by photomultipliers. Okay. So why? Because one look at Cherenkov light signals. So if the proton into positron pi0 decay occurs, then this positron here will produce a Cherenkov light in the water. Okay. But then the pi0 decays immediately into 2 gamma, and the 2 gamma can convert into E plus E minus pairs, and this E plus E minus can also produce Cherenkov light. Okay. So at the end, when Cherenkov light is formed in a cone, okay. And so when you project the cone in your layer of detector, at the end you get a ring. So the Cherenkov light forms a ring in the array of photomultipliers, and the specific event of a proton decay could be recognizable through the specific topology of rings that one observed in this photomultiplier array. Okay. Do you all know what is Cherenkov light?
Yes.
Anybody else? Okay, so
yes.
I guess you study already Cherenkov detectors. Okay, so this is the principle, right? Now, so we will come back to the proton decay in the very last lesson of the course. Okay, so we'll come back to this. Now, but at the moment, for now, the proton is stable. We don't have any evidence of proton decay. And so we don't have any evidence of baryonic number violating processes at the moment. Now, last time we have defined strangeness, the strangeness quantum number as of a hadron as the number of strange quark minus the number of anti-strange quark with a minus sign. There is another useful quantum number, which is defined for hadrons, but only for hadrons containing up, down, and strange quark, so let's say light hadrons, which is the so-called hypercharge, indicated with the capital Epsilon. And it is defined as the sum of the baryonic number and the strangeness. So the hypercharge of a certain baryon is given by the sum of these two quantum numbers. Now, since baryonic number is conserved in all interactions, as far as we know today, the hypercharge as well is conserved in those interactions in which also strangeness is conserved. So it is conserved in strong and electromagnetic, but not in weak interaction, because we know already that weak interaction violate conservation of strangeness. And as a note, the hypercharge of mesons, of course, coincides with the strangeness because the baryonic number of mesons is 0, as I told you before. Now, this rule that you find here, so this Gell-Nishi-Jima relation, relates the third component of isospin, I3, to the electric charge of the baryon and to the hypercharge of the baryon. So this you can write explicitly as the baryonic number and strangeness quantum number. So you can relate the third component of isospin with the electric charge, the baryonic number, and the strangeness of your hadron. We'll make an exercise about this. So, any questions? Okay, then let's solve some problems. This is the first one. So problem 5.4. So the sigma star plus is an unstable hyperon with a mass of 1385 MeV and a decay width of 35 MeV. It is produced in the strong reaction K minus proton into pi minus sigma star plus, and it decays into pi plus lambda 0 with a branching ratio of 88%, so with a very high probability into this specific channel. Now, 3 questions. The first one, is the decay of the sigma star plus into pi plus lambda 0 regulated by strong electromagnetic or weak interactions? Why the analogous reaction does not occur? Now we have a K plus instead of a K minus and a pi plus instead of pi minus. Otherwise, the rest is the same, but this reaction is not observed. Why? And using the fact that the lambda baryon here in the decay is an isospin singlet, determine the isospin of the sigma star plus. So I will now switch to the whiteboard. Give me 1 moment. All right. Can you see the whiteboard?
Yes.
Okay. So this is problem 5.4. So let's start with the first request. So is the decay of this sigma star plus regulated by strong electromagnetic or weak interaction? So the information we have is the decay width. So as usual, we have just to make use of the uncertainty principle. So we know that tau is h bar over gamma. We can multiply by the speed of light in the vacuum. And we know that now the numerator is approximately 200 MeV per Fermi. And in the denominator, we know from the text that the decay width is 35 MeV, and then we have to multiply by the speed of light in Fermi per second, that is 310 to the 23 Fermi per second. And the result you get is 1.9 10 to the minus 23 seconds. So, question for you, is this a strong electromagnetic or weak process?
Strong?
Yes, of course. So the decay time is so short that it can only be a strong process. And so, as we know, strangeness and isospin must be conserved. Okay. Now, the second question. So the second question is about why the other reaction cannot occur in nature. So let's first analyze this reaction here. So the reaction for the production of this sigma star plus is K minus proton that goes into a pi minus and sigma star plus. Okay, and it is a strong reaction, as we know from the text. Okay, So the strangeness has to be conserved in this reaction, and since the only strange objects are the kaon and the sigma, because the pion and proton, of course, have zero strangeness, then by strangeness conservation, it results that the strangeness of the sigma star must be equal to the strangeness of the K minus, right? And the K minus, if you remember, is a meson made by an anti-up quark and a strange quark. So the strangeness of the K minus is -1, and which is also the strangeness of the sigma star plus. We have a strange quark, so the strangeness must be -1. Okay. What about now the other reaction? So the other reaction is K plus proton into pi plus sigma star plus. Okay. But why don't we observe this reaction? So try to think a little bit.
The baryonic number is not conserved.
The baryonic number is conserved because both the proton and the sigma are baryons.
The strangeness of the K plus is +1.
Indeed, that's the answer. So the K plus is now a US bar system. Okay, so the strangeness of the K plus is now +1 because we have an anti-strange quark. Okay, so in this reaction we're gonna have a +1 strangeness here and a -1 here, as we derived before. So this reaction would require a delta S equal to, which is clearly not possible for a strong process. Okay, and this is indeed the reason why this reaction is not observed in nature. Okay, strangeness would not be conserved. Now, the last question was to calculate the isospin of this sigma star. Okay, so we know that from the text that this sigma star plus decays into a pi plus lambda 0, where a lambda 0 is an isospin singlet. So the isospin of the lambda 0 is 0. Isospin singlet. Okay. So since this is a strong decay, okay, as we deduce from the decay time in point A, okay, then of course isospin must be conserved. And so the isospin in the initial state, it is the isospin of the standard plus, must be equal to the isospin in the final state, which is only given by the pi plus, because the lambda is a singlet. Okay, well, I can also write here, but this is 0. And the isospin of a pion, we know it is 1. Okay, so overall, the isospin of this sigma star plus must be also 1. And in fact, the sigma star plus is a member of an isospin triplet, just much like the pions. So the triplet is the form. We have the sigma star minus, which is a DDS baryon. Then we have the sigma star 0, which is a UDS baryon. And then we have the sigma star plus, which is a UUS baryon. Okay, where of course the third component of isospin is -1, 0, and 1. This is I3. Okay. Okay, let's move on to the next. So we'll now go back to the slide. Okay, problem 5. So verify that the following hypothetical decays of the omega minus baryon conserve electric charge, baryonic number, strangeness, and third component of isospin. So we have 3 hypothetical decays for this omega minus meson. And we have also quite some information. So from each of these participants, we have the quark content, okay, and also the masses. And then the second question is why all these decays are actually forbidden. Okay, so let's see. All right, so this is problem 5.5. All right, so we have 3 decays. Let's start from the first one. And let's say an easy way to solve the point 1 is to make a table like this. So try to follow me. So here we put the initial, here we put the final, and here we put the match. Now, here we have the 3 the 3 particles. So for the first process, we have the omega minus that goes into proton plus 2k minus plus k 0 bar. Okay. Let me need one more. Let me take another. Okay, the total. And then we have the 4 quantities that we want to check. So we have the electric charge, the baryonic number, the strangeness quantum number, and the third component of isospin. Okay, so this is our first decay. So let's start now from the beginning. So the electric charge of the omega minus, okay, it is obviously -1. What about now the electric charge of the final state particle? So for the proton, it is of course +1. For the 2k minus, we have twice -1. And for the k0, it is a neutral meson, so it is 0. Okay, so the total in the final state is overall -1. And so it completely matches with the initial state. So electric charge is conserved. What about baryonic number? The omega minus is a baryon, so this is a +1. The proton is a baryon. And then the counts are mesons, so they have 0 baryonic number. So again, for the final state, we have +1, which corresponds to the initial state. What about strangeness? So the omega minus, as we see from the text, is a SSS baryon. Okay, so it's made by 3 strange quarks. So the total strangeness must be -3. Now, the final state, the proton has strangeness 0, the counts have twice -1, and the k0 is -1. So overall, in the final state, we also have -3, and so this is okay. Third component of isospin, the omega baryon has no up quark and no down quark, but only strange quark, so the isospin can only be 0. For the proton, we have, as we know, +1/2.
Sorry, why 0? Sorry.
Because the omega, because there are no up quarks and no down quarks, which are the only one that provides isospin.
Yeah, sure. Sorry.
Okay, so for the proton, we know is +1/2. For the 2 counts, it is twice -1/2. And for the k0 is +1/2. Okay, you can check with the quark content that you see in the information on the text. So also in the final state, it's 0, and so we have a perfect match. Now let me continue for the other 2 decays. So this in principle can occur. Now the other, so still QB. No, I need first to put So I need first to put the reaction. So this is 2, and then we have still omega minus in the initial state. Now we have lambda 0, k minus, a0 bar, total, and I get the match at the end. And now we have the electric charge, baryonic number, strandedness, height 3. Okay, so for the initial state, we can just copy the one from the previous column. So we have -1, +1, -3, and 0. Let's now work out the final state. The lambda 0, the electric charge is clearly 0. It is a neutral baryon. For the K minus, it is -1. For the K meson, neutral is 0. So again, this is -1, and again, we have a perfect match. What about baryonic number? The lambda is a baryon, so we have a +1, and the other two are mesons. So it is +1, and again, we have a match. Strangeness. The lambda is a UDS baryon, so it has one strange quark, so this is -1. The K minus is also -1, and the K0 bar is also -1. So we have -3, and again, we have a perfect match. Isospin. The lambda is, as we saw before, is an isospin singlet, so it has 0. And then we have -1/2 for the K minus and +1/2 for the K0 bar. So again, 0, and again, perfect match. Let me go now to the last one. So omega minus that goes into xi 0 K minus. So we still have Q, B, S, 3, -1, +1, -3, and 0. Okay, so the sigma, the Xi0 particle is a USS baryon. So what we have, first of all, electric charge is 0, and the electric charge at the count is -1, so it is -1 and match, perfect match. Baryonic number, the Xi, is indeed a baryon, so we have a +1. The K is a meson, so we have 0, so +1 and match. Strangeness. So we have two strange quark here in the Xi, so this is -2, -1 from the chaos, so again -3, match. And finally, this isospin. So it is, we have one up quark in the Xi, so it is +1/2. And then we have one U-bar quark in the K minus, so it is -1/2. So this is 0, and again, perfect match. So based on this quantum number conservation, all three decays are possible, okay? However, they don't occur in nature. So can you try to say why? You have to better look up at the, okay, I will project the slide again. Okay, so based on the information you have on the text, can you say why all these decay cannot occur?
Energy conservation?
Yes, indeed. So let's see why. I go back now to the board. Okay, so indeed the problem is about energy conservation. So let's consider the first decay. So the first decay was omega minus into proton plus 2k minus plus k0 bar. Okay. Now, the mass in the initial state, that is the mass of the omega, is 1672 MeV. What about the mass in the final state? So we have the mass of the proton plus twice the mass of the kaon plus the mass of the K0. That is 988 plus twice 493 plus 498 MeV. That is 2422 MeV. Okay, so the mass in the initial state is smaller than the mass in the final state. So energy conservation will be violated. Okay, we don't have enough energy in the initial state to allow this to decay. Okay, and this is the same reasons also for the other two. This you can check yourself by plugging the numbers. Okay, so so how does this omega minus baryon decays actually? Okay, so the only possible decays for these omega minus baryons are regulated by the weak interactions, and indeed they violate the strengthness conservation. So the main decays modes are the following: omega minus into say 0 pi minus, okay, and this has a branching ratio of 23.6%, okay. So in the initial state we have a strangeness of -3, in the final state we have a strangeness of -2, so there is a delta S of 1, which is allowed by weak interactions. Okay, another decay mode is the psi minus pi 0 with a branching ratio of 8.6%. Again, we have here a delta S equal 1 for the same reason. And the last one, the one that I just quote here, there are many more, of course, is lambda 0 K minus with a branching ratio of very large, 67.8%. And so again, we have a delta S equal 1. Okay. All right. Let's move on to the last problem. No, actually two, still two. Okay. So problem 6. So find at least one conservation law, invariance principle, or other mechanism which is responsible for suppressing or forbidding the following decays. Okay. So let's now treat them one by one. Okay, so this is problem 5.6. Okay, so let's start from the first one. The first decay is a K plus into pi plus, pi plus, pi 0. Okay. Do you see a reason why this decay is forbidden?
The charge conservation.
Exactly. So in the initial state, we have a +1. In the final state, we have a +2, which is different than Q. So charge conservation is violated. Let's take the second one. K plus into pi plus, pi minus, pi plus, pi minus, pi plus, pi 0. So initial state charge is +1. Final state is 1 minus 1 plus 1 minus 1 plus 1 plus 0, that is plus 1, which corresponds to the initial state. So charge conservation is not the problem. What is the problem here? Hello?
The energy.
Ciao,
Go ahead.
Benjamin. I guess energy conservation here.
Yes, exactly. Right. The initial state mass is the mass of the kaon, that is 494 MeV, and the final state mass is 6 times the mass of the pion, which is 140 MeV. So this is of the order of the 840 MeV, which is greater than the initial state. So energy conservation. Is violated here. The next one, lambda 0 into K0 plus K0. So the initial charge is 0, the final charge is also 0. The initial mass is the mass of the lambda baryon, that is 1115 MeV. The final mass is the mass of the K0 plus the mass of the pi 0, that is overall 633 MeV. So energy conservation is fulfilled. What is the problem here?
Baryonic number?
Yes, correct. Initial state we have a baryon. Final state we have only mesons. So it's baryonic number violations. Okay, let me take a new sheet. Now we have the psi minus into neutron plus pi minus. So initial charge is -1, final charge is 0 minus 1 equal -1. So okay. Let's check energy conservation. The initial mass, the initial is the one of the psi minus baryon. It is 1322 MeV. The mass in the final state is the mass of the neutron plus that of the pion, so it's 939 plus 140, so this is order of 1080 MeV, which is smaller than the initial mass, so energy conservation is okay. Let's check baryonic number. Baryonic number in the initial state is 1 because we have a baryon, but also in the final state we have 1 plus 0 equal 1. So baryonic number is conserved. Let's check isospin. So the isospin in the initial state is 1/2. In the final state, we have to compute In minus I pi minus IF In plus I pi minus. That is 1/2 minus 1 smaller than I, smaller than 1/2 plus 1. And so in the final state, we can have either 1/2 or 3/2. So in the initial state, we have 1/2, but in the final state, 1/2 is also possible, okay, because we have two possibilities, including 1/2. So in principle, the decay can occur through the common value pi 1/2, okay? So we don't have an answer yet. Let's look now at the third component of isospin. In the initial state, this is minus 1/2. In the final state, we have minus 1/2 for the neutron, minus 1 for the negative pion. So this is minus 3/2. That is different from the initial one, right? So the process cannot be strong because the third component of isospin is violated, nor electromagnetic, but can still be a weak process. Okay. So why does this not occur anyway? So let's check the strangeness. So the strangeness in the initial state is -1. We have two s quarks in the psi minus baryon. The strangeness in the final state is 0 because it's 0 on the neutron, 0 on the pion, so it's 0. So we have a delta S equal to. Now, delta S equal to is a violation of strangeness. Okay, it's a strong violation of strangeness, but still this is in principle allowed by weak interactions. Weak interaction can violate whatever thing. Okay. The problem here, and this we will study next in the course, so we probably cannot understand at the moment, is that in order to get this decay, you need to transition from the S quark into the D quark. That's why we get a strangeness gap of 2. Okay, but this kind of transition are so-called flavor-changing neutral currents, because they come with let's say the charge is conserved. We have -1/3 for the strangeness and -1/3 for the down quark. So these are neutral currents, weak interaction neutral currents, with the flavor changing. And as we will study, okay, next at the proper time, these are suppressed processes in the standard model. So they cannot occur at 3 level, so at 0 order in the perturbation, can only occur in higher, more complex, higher order diagrams. And here you actually need 2 of them. So it is possible, but strongly suppressed. So the reason will be clear in a few weeks from now, okay? And in fact, the branching ratio for this decay is smaller than, we have an upper limit, 1.9, 10 to the -5. Last one, so let me take a new page. Pi 0 into gamma, gamma, gamma. Okay. So quickly, electric charge is 0 everywhere, so it is conserved. Okay. There is no problem with energy conservation because we have a massive pion decaying into 3 massless objects, which are the photons. Baryonic number is 0 everywhere. We have bosons everywhere. Strangeness is 0 everywhere, so it is conserved. Let's consider now isospin. In the initial state, the isospin is 1, the isospin of the pion. In the final state, the isospin is clearly 0. Okay, so isospin is not conserved, but this is still okay for electromagnetic processes and weak processes. What about the third component? Third component for the pi 0 is 0, as we know. Okay, third component in the final state is clearly 0. So E3 is conserved. So again, this is okay for an electromagnetic decay. So why we don't observe this decay? Let's check parity. The parity in the initial state is -1. The parity in the final state we have to combine, because it's a pseudo-scalar meson. In the final state we have to combine the parity of the 3 photons, so it's -1, L12 plus L3, times the intrinsic parities of the photons, which is negative, if you remember. Okay, so overall this is -1, L12 plus L3 plus 1. So the final state parity can be equal to the initial state if L dot is, so L12 plus L3 is even. So still possible. So why does this decay cannot occur? Okay, I'll tell you. It's about charge conjugation. The charge conjugation in the initial state for the one with the pi zero is, if you remember, +1, because the pi zero is an eigenstate of the charge conjugation operator with eigenvalue +1, if you remember. In the final state, we have -1 to the cube, that is -1. So charge conjugation is violated. Okay, and this cannot be in electromagnetic processes. Okay, so this is indeed the only reason why this decay is not observed in nature. Okay. Now, very quickly, actually, the last one you can do as an exercise. Okay, it's so easy that you can just play yourself with the last problem. So using the Gell-Mann-Nishijimi relation, check that the I3 assignment for the following hadrons is correct. Okay, so you just have to use the Gell-Mann-Nishijimi relation that I provided in the slide. You substitute the values of the charge, the baryonic number, the strangeness, and then you verify that you obtain the correct value for the third component of Isospin. Okay, let's make a short break. Not too long, because then we are out of time. So let's combine at 22, okay? 12:22.
Okay, thank you. Professor, can I ask you something?
Of course.
Could you please upload the new slides that you have shown us with the Clebsch-Gordon
Yes.
part? Okay, thank you very much.
I will upload today together with the scan of this. Yeah, sure. And I will also upload the few slides from the muon magnetic moment in the QED chapter.
Perfect.
Okay, sure. So see you in 5 minutes. Ok, I think we can start. Ci siete, ragazzi? Mi date un cenno?
Sì, ci siamo, prof.
Yes.
Ok, ok, vedete la slide anche, giusto?
Sì.
Ok. So, so we learned quite a lot about isospin and strangeness, which are the quantum numbers that affect, let's say, the lightest quarks, the up, the down, and the strange. So for the moment, we will stay with these light quarks. We will introduce the heavier quarks next time. But we will now extend our formalism, the isospin formalism, to also include strangeness. Okay, and this is all about the so-called quark model. Let me make some historical introduction to this. So the particle that you see here, which are essentially 8, 9, whatever, 8, no, 7, actually 7, plus or minus. So these are the only particles that were known until 1950. Okay, so the electron was discovered by Thomson back in end of the 19th century in the cathodic tubes. The proton by Rutherford in this famous nuclear reaction. The neutron by Chadwick in 1932. The positron, as we studied, by Anderson. Okay, which supported the Dirac theory, if you remember. The muons and the pions in cosmic rays. We also discussed this. And also the kaons were found in the Rothschild-Butter experiment that we discussed last time, again, studying cosmic rays. So this was the situation. It was quite simple situation until 1950, okay? So few particles that can also be all, in principle, all fundamental, all elementary particles. However, with the advent of the particle accelerators after the Second World War, so after, let's say, the 50s, tens and tens of new particles were discovered in a matter of 10, 15 years. Okay, so actually something like 100 of new particles were discovered in 10, 15 years. And now it becomes, of course, hard to believe that all these particles are elementary particles. Okay, it would be very strange that nature would have chosen so many different elementary bricks to build up our matter. However, it was soon realized that hadrons having the same JP quantum numbers, where P is parity, they could be grouped into multiplets. Okay, and these multiplets can be represented in the hypercharged third component of isospin plane. And you see here some examples. So you have the hypercharge in the vertical axis, the third component of isospin in the third axis, and then you can group your hadrons based on the JP quantum numbers, and you see that they form the multiplets. Okay, they form multiplets. Now, these regularities were suspected to be the manifestation of some internal degrees of freedom. So in other words, hadrons must have an internal structure that cannot be elementary objects. Okay, and this suspect soon evolved into the Quark hypothesis. So the Quark hypothesis, what we also call the static Quark model, was proposed independently by Gell-Mann and Zweig in 1964, and indeed provide an elegant solution to the puzzle. So hadrons are indeed composite systems made by elementary objects that they call quarks. Actually, Gell-Mann called them quarks, which come with a fractional electric charge in order that the hadrons that we observe have an integer electric charge. Okay. So now, until 1974, only 3 quarks were known: the up, the down, the strange. So the original Quark model includes only those quarks, only those quark flavors. And the charges are plus 2/3 for the up quark and minus 1/3 for the other 2 down the strange. And according to the Quark model, quarks are subject to the strong force and form bound states that we call hadrons, okay, with integer electric charge, and this happens in 3 different ways. So either baryons, which are made by 3 quarks, anti-baryons, which are made by 3 anti-quarks, or mesons, which are quark-anti-quark pairs, essentially. Quark-anti-quark bound states. Now, the correspondence between the experimentally observed hadrons and those predicted by the Quark model, of course, constitute one of the strongest arguments for the existence of quarks. Okay, then we will study next that the final proof is when you indeed experimentally test them. This is another story we will study next. just to make some fun, this is so Gell-Mann expired a couple of years ago. Okay, and this is a nice picture of his house and his car, and look at the tablets here. So the regularities of the observed hadron can be understood in the framework of the Quark model and find a physical justification in the flavor symmetry of strong interactions. So strong interaction, this means that strong interaction treat all quark flavors in the same way. Okay, and therefore the Lagrangian of the strong interaction must possess an exact flavor symmetry. Okay. Now the isospin symmetry that we already studied is a manifestation of the more general flavor symmetry when this flavor symmetry is restricted to the case of the two lightest quarks up and down. And as we studied, the isospin symmetry is an almost exact symmetry because the difference of the up and down mass is very small. Okay. Also, the difference between the proton and the neutron mass is order of 1.2 MeV, but it's very small. And this difference is very small compared to the mass of hadrons. Okay. So the electromagnetic interaction is the only responsible for this mass difference, and it represents only a small contribution to the overall interaction Lagrangian. So our total Lagrangian is the unperturbed and the interacting part. The interactive part we can split in three terms according to the three fundamental interactions. And as we know, the strong one dominates by definition, and then electromagnetic and weak are, of course, smaller, okay? Much smaller. So in principle, it is possible to extend the isospin symmetry to a more general symmetry that also includes the strange quark. And this is what we call the flavor symmetry. There is a caveat. So the point is that the mass of the strange quark is now 96 MeV, okay? So it is very different from the masses of the up and down quark, which are of the order of few MeV, okay? So indeed, when one includes also the strange quark, the overall Lagrangian is manifestly not flavor symmetric, okay? So it is a Proton symmetry. However, the difference between the up and down masses and the mass of the strange quark is still relatively small, order of 100 MeV, compared to the typical masses of baryons, which are above 1 GeV. Okay? So one can reasonably assume that the overall Lagrangian does possess an approximated UDS flavor symmetry, which is, of course, less exact than the isospin symmetry, but still a reasonably good one. Okay, so this is, let's say, our starting point, our assumption. Let's now introduce the formalism. So in analogy with isospin, this flavor symmetry can be expressed by a unitary global SU3 transformation in the flavor space. Okay, where the transformation is given in this way, where U is a unitary operator, where now these alpha I are 8, so I go from 1 to 8 global parameters. We don't have any dependence on the space-time coordinates of the transformation, and these lambda I are the corresponding 8 generators, which are conventionally chosen to be the 8 Gell-Mann matrices that you find here. Okay, so in other words, these 8 Gell-Mann matrices are the generalization at the level of SU3 of the 3 Pauli matrices at the level of SU2. So indeed, in analogy with the 3 Pauli matrices, these 8 independent unitary tracelet matrices form a fundamental representation of the SU2 group. Let me remind you that the dimension is n squared minus 1, so it is 9 minus 1 equals 8. That's why we have 8 generators and 8 parameters. Okay, and we call this symmetry group as the SU3 flavor, or simply SU3F. Okay. It is important to specify F in order not to make confusion with the SU3 color, which is instead, as we will study, the exact symmetry of quantum chromodynamics. Okay, and that is a global one. It is a local one. So they are completely different stories. Now, so the SU3 flavor group contains the SU2 up-down isospin subgroup. Okay, and in fact, you can see already these into the Gell-Mann matrices. So the first 3 Gell-Mann matrices have the Pauli matrices in the top left 2 by 2 block. Okay, T1, T2, and T3. Well, all the other elements are equal to 0. Okay, and the remaining gamma matrices can be lambda matrices can be identified by realizing that the SU3 flavor group also contains, of course, the other combination. So this is U into D, but we also have, once we add the strange quark, we also have U into S or D into S. Okay, both of which can also be expressed in terms of Pauli matrices, of course. So essentially, the isospin group is a subgroup of the flavor symmetry group, in other words. Now, for the isospin, we define two basis vectors, U10 and D01, if you remember. Now, of course, here we have an additional degree of freedom, so we need to introduce flavor triplets. So these are the three eigenstates: 100, 010 for the down, and 001 for the strange quark. Okay, and it turns out that these are simultaneous eigenvectors of the lambda 3 and lambda 8 Gell-Mann matrices. The corresponding eigenvalues are related to the third component of isospin and to the hypercharge through these operators. Okay, so the third component of isospin is related to the lambda 3 Gell-Mann matrix, and the hypercharge is related to the lambda 8. Is related to the lambda 8 Gell-Mann matrix. So let's check these quickly on the board. Okay. So our operators are indeed tau3, that is 1/2 of the third Gell-Mann matrix, and y, that is 1/√3 of the 8th Gell-Mann matrix. Okay. So let's now calculate the eigenvalue equation for the up quark state. This is 1/2. Then we have the third Gell-Mann matrix. It is 1, 0, 0, 0, -1, 0, 0, 0, 0, acting on the up quark state, that is 1, 0, 0 in this space. So when you make now the matrix vector multiplication, you obtain the vector itself. So it's 1, 0, 0. And so you obtain plus 1/2 U. And in fact, the third component of isospin for the up quark is indeed plus 1/2. Okay. Then you can repeat the exercise for the other two. So when you do for the down quark, okay, I will skip the intermediate passages. We're gonna have -1/2 D. And when you do this for the strange quark, what do you expect for the strange quark to be? Hmm?
0, maybe.
Yes, it must be 0. The isospin of strange quark is 0 indeed. Okay. What about now the other operator? So the hypercharge operator acting on U, it is 1/√3, and then we have the 8th Gell-Mann matrix, which also include the 1/√3 factor, and then we have 1, 0, 0, 0, 1, 0, 0, 0, -2, acting on the up quark, that is 1/3, 1, 0, 0, that is plus 1/3 U. So indeed, the hypercharge of the U quark is plus 1/3. And then you can repeat the exercise for the down quark. You're going to get again plus 1/3. And for the strange quark, at the end, you're going to have 1/3 of 0, 0, -2. That is -2/3 of 0, 0, 1. That is -2/3. So in other words, the eigenvalue of T3 for the up quark eigenvector corresponds to the value of the third component of isospin for the up quark, and the same for down and strange. And the eigenvalue of the upsilon operator for the up quark eigenvector corresponds to the value of the hypercharge for the up quark, and etc. The same for all the others. Okay. So let's now summarize all these results in a table. Okay, before that, let me just say something more. So we now switch to the slide. So these eigenvalues are, of course, in agreement with the values provided by the Gelman-Gini relation. Okay, so the one you have to apply in your homework exercise. Okay, once you put B quark 1/3, the charge of U quark plus 1/3, the charge of the down and strange quark minus 1/3, and strangeness of up and down 0, and strangeness of OS minus 1. Okay, so you can verify this. Now let me summarize the results in this table. So we have 3 quark flavors, up, down, and strange. They are all spin 1/2 fermions. They all have the same 1/3 baryonic number. This is the electric charge. This is the third component of isospin, plus 1/2 for the up quark, minus 1/2 for the down quark, and 0 for the strange. Then we have the strangeness, which is, of course, 0 and 0 for the up and down, and minus 1 for the strangeness. And then we have this hypercharge, okay, that we just calculated. It is 1/3, 1/3, and minus 1/3. So we can now represent this quark triplet in the space spanned by the hypercharge and the third component of isospin, okay, like this. So we put here the third component of isospin in the x-axis and the hypercharge in the vertical axis. And so just by taking these values here and these values there, we can locate our 3 quarks flavors, okay? So the up quark has isospin 1/2 and hypercharge plus 1/3. The down quark has isospin minus 1/2 and hypercharge plus 1/3. And the strangeness has isospin 0, so it stays in this axis, but with an hypercharge minus 2/3. And this is the quark triplet. What about antiquarks? So when we switch to quark to antiquark, as I mentioned several times, we not only change sign to the electric charge, but also to the internal quantum numbers. So essentially, all these quantum numbers become opposite, okay, when you switch from quarks to antiquarks. So we can now represent the antiquarks in the same plane. Now the S bar sits here, and the up and down are there, okay? Let me remind you that the third component of isospin is also switched between up and down, because the D bar is more positively charged than the U bar. And now we can combine them to make mesons, okay? So the combination of a quark triplet and an anti-quark triplet, so 3 times 3 bar, okay? If you apply group theory, this results in an octet plus a singlet. So the situation is represented here, okay? So when you combine a quark triplet times an anti-quark triplet, theory group tells you that you will obtain an octet of states plus a singlet. And you see also here now the flavor, the composition of each of these states, okay? So a few comments. The 8 octet states transform among themselves under SU3 flavor rotations, but in principle, they do not mix with the single state. Of course, this is only true if one assumes an exact symmetry, an exact SU3 flavor symmetry, which is, we know already, not the case. We know that the symmetry is partially broken, okay? So we should expect already now that there could be mixing between the octet states and the singlet states, and this we will see later. The singlet state corresponds to vanishing third component of isospin and hypercharge. And this can be thought as essentially flavorless state, in the sense that they carry no information about the flavor of its constituents. And in fact, you have each flavor and each anti-flavor altogether, okay? So this is essentially a flavorless object. Now, let's think a little bit about mesons. So mesons are bound state of a quark and an antiquark, as we know, okay? Now, of course, each quark and antiquark has 2 possible spin states. Okay, so when we combine the spin for a meson, we know that we can get either an S = 0 singlet spin state or an S = 1 triplet spin state, as we studied. What about now the total angular momentum? So for the lightest mesons, the lattice mesh corresponds to a vanishing orbital angular momentum, and this we already named as low-lying states, if you remember. Okay, so the low-lying states are essentially the the ground state meson, so those that come with the vanishing orbital angular momentum. And so the total angular momentum, which is L plus S, can only be given by the spin for low line states. Okay, and so this can be either 0 for the case of a spin singlet or 1 for the case of the spin triplet. What about the parity? So the parity of a QQ-bar system is -1 to the L times the intrinsic parities of quark and anti-quark. Okay, and we know that these are opposite in sign. So overall, this is -1 to the L plus 1. But for low line states where L equals 0, then we always get a minus sign here. Okay, so all low line states must have odd parity. Now, considering all the possible combination of flavors and spins, one obtains 9 light JP equals 0 minus pseudoscalar mesons and 9 light JP equals 1 minus vector mesons, where each category is composed by an octet and a singlet. So what we have here? 0, because it is the case where we consider singlet spin states, and minus because the parity is always negative, okay, for low-lying mesons. So these are called pseudo-scalar mesons. Pseudo because we have a negative parity, odd parity. And the other 9 are vector mesons. Vector because we have now spin 1, so they are vector particles, and still we have a negative or odd parity. So let's look at them more into detail, okay? So what is represented here is now the octet states for the JP 0 minus and for the JP 1 minus. So the pseudo-scalar mesons and the vector mesons, low-lying states. So what we see here is that we have 2 isospin doublets. One is here, K0, K plus, the other is there, K minus K plus, K minus K0 bar, okay? So they come with 2 opposite projections of the third component of isospin. Then we have one isospin triplet, the pi minus, pi 0, pi plus, or for the vector meson, the rho minus, rho 0, rho plus. And then there is one isospin singlet, that we call eta 8 or phi 8 here. And in total, we have 2 states which have vanishing third component of isospin and hypercharge, which are the pi 0 and eta 8 for the pseudo-scalar mesons, and the rho 0 and phi 8 for the vector mesons. Okay. In addition to that, we have the singlet, okay, because it is always an octet plus a singlet, and the singlet is, of course, with vanishing I3 and Y. So let me stop for a while here. Do you have any questions? Seems not. So we can go ahead here. So let's now focus on these 2 E30 hypercharge 0 octet states. Okay. So for the pseudo-scalar meson, these are named the pi 0 and the eta 8, and this is their flavor decomposition for the 2. Okay. Retro pion and this eta 8 meson. Now, what about the singlet? Okay. The singlet, it is called eta 1, just to differentiate from eta 8. And this is its completely flavorless flavor decomposition, as we saw before. Right? Now, what is now the peculiarity here? The thing is that the eta 8 and the eta 1 mesons are not observed in nature. Okay. What one observes are 2 different objects that we call eta and eta prime, which are actually linear combinations of eta 8 and eta 1. And so they result from the mixing of a singlet state and an octet state. Okay? So this pure state we don't observe in nature, but we observe the mixed state, where mixed means that there is mixing between the octet and the singlet state. And of course, this is only possible because the asymmetry figure symmetry is not an exact symmetry. If it were an exact symmetry, you could not have this mixing, and you must have observed in nature the eta 8 and eta 1. Now, the correct description of this complicated mixture of quark, antiquark pairs, and gluons can be achieved only within the theory of quantum chromodynamics. So far beyond this simple static quark model. Furthermore, if the SU3 symmetry were an exact symmetry, then one should expect that the pi0 and the eta meson would have exactly the same mass. Okay, it is more like if the isospin symmetry was an exact symmetry, then the proton and the neutron should have exactly the same mass, which is not quite the case. However, since we know that the mass of the strange quark is much larger than that of the up and down, their mass is very different. So the mass of the pi0 is 135 MeV, and the mass of the eta is something like 3 times larger. Okay. The mass of the eta prime is even larger, so order of 1 GeV, and again, this can only be understood in the framework of quantum chromodynamics. What about the vector mesons? So this is now the octet of the vector mesons. Okay, we have also the corresponding singlet, which is not reported here. So in the case of vector meson, the mixing between these the state with vanishing quantum numbers from the octet and the singlet, so the phi8 and phi1, is even more pronounced than for the pseudoscalar mesons. Okay, so this is the flavor combination for the phi1 and phi8, and instead what one observes in nature are these combinations. So the phi meson and the omega meson, these are not observed in nature, okay, but only their combination. And this is indeed the combination that we can express in terms of a rotation matrix by a certain angle, which is a mixing angle, which is quite large for the case of vector meson. So it's over 35 degrees, compared to 11 degrees for the case of pseudoscalar mesons. So in other words, the fact that SU3 flavor is not an exact symmetry allows for mixing between octet states and singlet state. And indeed, the meson that we observed with these vanishing quantum numbers are indeed the result of this mixing in both cases, for vector and pseudoscalar. So these observed states corresponds to the ρ0, the omega, and the phi. Okay, and if you look now at the quark content, so UU bar minus DD bar, UU bar plus DD bar, and SS bar, these explain why the omega and the ρ have essentially the same mass, order of 770 or 80 MeV, whereas the phi meson is something like 300 MeV more heavy, so order of more than 1 GeV. Okay. Now here we summarize a little bit the properties of the low-lying pseudoscalar mesons. So we know already pretty well the pions. The pi plus and pi minus decay with a lifetime typical of the weak interaction into indeed final state that include neutrinos. So these are pure weak processes, of course. The pi0 instead has a much shorter decay time, and this is because the decay occurs through the electromagnetic interaction into 2 photons with a 99% branch interaction. Then we have the kaons. So we have the charged kaons, which behave pretty much like the charged pions. So again, we have decay time typical of weak interactions. And these are some of the main decay modes. And then we have the neutral kaons. So here you see a different notation, the k short and the k long, S and L. And as we will study next in the weak interaction chapter, we will see that actually the k short and k long are combinations of the k0 and k0 mesons. Okay, so this we will study next, why we call it this way. And then we have again now all these decay mode. Then we have now the eta and eta prime, which only decay electromagnetically into either pions or photons or whatever here. What about the vector mesons? So we have the 3 rows, ρ minus, ρ0, and ρ plus. You see now the decay time is typical of the strong interaction, is for all of them here. And so the ρ decays in 2 pion with 100% probability. Same for the k star in a kaon pion, and for the omega. And then there is an interesting feature for the phi meson. Okay, it is still a strong process, but you see now the decay time is a bit longer, and it is because this decay has a component which is suppressed. So in which sense it is suppressed? So the 2 main decay modes of the phi meson are 2 kaons or 3 pions, and these are essentially the diagrams for these decays. Okay, so in the first case, we have an S bar system that pick up a UU bar quark pair from the vacuum, then the S combined with the U bar providing a K minus, and the S bar combines with the U, creating a K+. Okay. In this case, for the pions, we have an SS bar diagram, which at the end, by picking up two pairs of DD bar quarks from the vacuum, once obtained a pi plus, a pi zero, pi minus. Now, let's look at energy conservation, okay, in this process. So the Q value, so the energy available in the decay, if you like, the final state energy, okay, the one that we studied in the Fermi-Golden rule, as you see, is extremely small in the case of the decay into K minus and K plus, is only 24 MeV, because the mass, if you sum the mass of the two, you almost obtain the mass of the phi, where the energy available in the decay is much, much larger for the case of 3 pions, which are much lighter, okay, or the 6 MeV. So from the pure kinematic point of view, or from the pure phase space point of view, one would say that the decay of the phi into 3 pions should be much more favored than the decay into the 2 kaons, because we have a much, much wider phase space available in the final state. However, as you can see here, one finds the opposite. So the decay into the 2 kaon is much more probable than the decay into the 3 pi. Okay? So the suppression of the 3 pi mode is a consequence of the fact that this decays, as you can see here, involves disconnected lines. There is a gap here, okay? And as we will study next in QCD, okay, the disconnected diagrams like this one are indeed suppressed by this rule, which is called the Okubo-Zweig rule, okay? So we will come back to this issue in the QCD chapter, and we will understand where is the problem here. Now, a question. So I have another argument for today's lesson, but we have only 5 minutes. So I ask you whether you want to continue. This will take another, in total, 10-15 minutes, or you want to stop here and then we continue next time. Just tell me. So the remaining argument is about the mass of mesons, and this will close the chapter of mesons. Then next time we will start with baryons. Otherwise, if you have to go to lunch now, we can interrupt now. Let me know.
It's okay for me.
Okay to continue or okay to stop?
Okay to continue, I mean, for me. I don't know for...
Okay, what about the others? Allora? Continuiamo altri 10 minuti o stoppiamo adesso, ragazzi? Ditemelo, pensateci un attimo.
It's okay to continue for me.
Ok, opposite question. Qualcuno deve scappare adesso, altrimenti continuiamo 10 minuti.
I think it's okay to me too.
Oh. Vabbè, se non sento, diciamo, rivolte dal basso, allora continuo. Okay, so let's go on quickly to the last topic today. So this is about now the mass of the mesons. So the measured mass of the ground state mesons are reported here. So we have here the pseudoscalar mesons with the mass and the vector meson with their masses. Okay. Now, once more, if SU3 flavor symmetry were exact, then all the state in the pseudoscalar mesons octet would have the same mass. So all these mass will be the same, and also this one will be the same. Okay. And as we know, we observe the mass difference derived from the fact that the quark strange is significantly more massive, and so this breaks the SU3 flavor symmetry than compared to the up and down quark. So it is not a surprise. We know that now these masses are so different. Okay. However, this does not explain why the vector mesons are more massive than the pseudoscalar mesons. If you compare, for instance, the flavor wave function, okay, for instance, for the pions and the rolls, they are exactly the same. So there is in principle no reason why the vector mesons should be heavier than the corresponding pseudoscalar mesons. And the difference is quite large, okay, in the order of 600 MeV. So what is the difference? The only difference is spin, indeed. One is scalar, one is vector. Okay. So the only difference between pseudoscalar and vector meson is their spin. And in fact, the different masses of the pi0 and rho mesons, and in general between the pseudoscalar and vector mesons, can be attributed to a spin-spin interaction, which is known as the chromomagnetic interaction. So let's see what is this about. So the chromomagnetic interaction depends upon the relative orientation of the quark and the anti-quark spin, and correspond to a spin-spin term in this phenomenological QQ bar potential. So what do we have here? First of all, alpha S is the coupling constant of QCD, as we will study. So it is the equivalent of alpha electromagnetic, but now for the strong interaction. Then we have a Dirac delta function, which ensures that all this term here is large only at short distances. So only when x is essentially close to 0. Otherwise, this delta kills everything here. Okay, where x is the relative distance between the quark and the anti-quark. Okay, so we have in our phenomenological potential, we have a term which depends now on the relative spin orientation of these two objects. Okay, we have a scalar product here. Then we have the masses, and then we have alpha strong and this delta Dirac. Now, a similar effect is also observed in QED, and is indeed responsible for the hyperstring splitting of the atomic energy levels, as you already studied. However, there is a big difference because the alpha strong coupling constant is much, much larger than the electromagnetic. So this is order 1, and the electromagnetic is order 1 divided by 137. And so the chromomagnetic interaction is much stronger in QCD than in QED. And in fact, it is responsible for the different masses that we observe, here. Whereas the effect on the QED is only visible in terms of hyperfine splitting in the atomic energy levels. Now, as we've seen before, the chromomagnetic potential vanishes at large distance. So it only applies when these two quark pairs are extremely close, so where x is close to 0, okay? And so if you now look at the orbitals, okay, this implies that this term is only relevant for L equals 0. Because the L equals 0, so the S wave is the only one which have a non-zero probability that the two quarks stay at 0. Okay. Otherwise, in the P wave, D wave, we always a node here in 0. So they are more separated, and so this term becomes essentially negligible. And that's why this term here is relevant only for the low-lying mesons. Okay. Now, for an L equals 0 meson formed by a quark and an anti-quark with mass m1 and m2, the meson mass can be obtained through this phenomenological formula. So, suppose you have a system of two quarks. The mass is given by the sum of the masses of the two quarks plus a term which includes this spin-spin interaction. Okay. Here, alpha is a parameter which is proportional to the wave function at 0. Okay, and alpha strong, and this must be determined experimentally. So let me quickly show you how to calculate now this expectation value. Okay. So this this is a simple algebra that you know already from quantum mechanics. So the total spin is the vector sum of spin of one particle plus spin of the other particle, S1 plus S2. So when you take the square of this is S1 squared plus twice S1 scalar S2 plus S2 squared. Okay. So you can invert these and you can extract the scalar product, S1 scalar S2. And this is equal to 1/2. And then we have S squared minus S1 squared minus S2 squared. Now you take the expectation value of this, S1 scalar S2. The expectation value is given in terms of the expectation values of these operators. That is, now you can put here the eigenvalues. So it's S plus 1 minus S1 plus 1 minus S2 plus 1. So this is the master formula. Then we have to substitute our numerical values. So since we are dealing with the quarks, so S1 is equal to S2 is just 1/2. And now we are combining two spin 1/2 objects. So the total S can be either 0 for the pseudoscalar mesons, so they stay in the spin single state, or 1 for the vector meson. And so we can now compute this expectation value for the two cases. So S1 scalar S2, this is, let's just substitute the numbers. So 1/2. Then we have, this is for the pseudo scalar, yes. So this is 1/2, 0 minus 1/2 times 3/2 minus 1/2 times 3/2. That is 1/2 minus 2 times 3/4. That is minus 3/4. And the expectation value for the case of the vector mesons is 1/2. Now we have 1 times 2, times 2 minus 1/2 times 3/2 minus 1/2 times 3/2. This is 1/2, and then we have 2 minus 2 times 3/4, and it is at the end 1/4. Okay, so overall we get these two numbers, minus 3/4 for the pseudoscalar mesons and plus 1/4 for the vector mesons. So let's go back to the slide and substitute these results into the master formula. So for the pseudoscalar mesons, when S is equal to 0, we get this minus 1/4 here. Okay, so the formula gets this shape. For the vector meson with S equal 1, we get this plus, so this was minus 3/4 and plus 1/4 here. Okay, so these are the two formulas for calculating the masses of pseudoscalar and vector mesons. And as already you see from here, we have a plus sign here and a minus sign here, so it is already clear by comparing these two formula that the mass of the pseudoscalar mesons must be smaller than those of the spin 1 vector mesons. Okay, so this mass difference is indeed due to this chromomagnetic interaction. Let's now compare the experiment with the calculation based on this formula. So again, these are our pseudoscalar mesons and vector mesons. So the experimental value are reported here for the masses, and these are those that you calculate with this formula. You see, they are incredibly close. You see? So this formula, which is phenomenological, is at the end a quite accurate one. And it is actually highly surprising that there's simple phenomenological formula that do not take into account any formal dependence on the quark color dynamics, so on QCD. They describe so well the mesonic spectrum at the 1% level or even better. Okay, and this is indeed an unexpected success of the quark model. There is only one exception here, that is the eta prime, which is not reported here. The predicted value is quite smaller, is 355 MeV, to be compared with almost 1 GeV. Okay, so this differs significantly from the anomalously large observed value. And the reason for this discrepancy is attributed to the fact that the omega prime is a flavorless state. And so as such, it can in principle mix with the purely gluonic objects that are called the glue balls. So from the QCD point of view, the structure of the eta prime can be much, much more complicated than other mesons. And this is why, in this case, the simple quark model fails. What should we put here for the masses? So in the formula, we have to put the value of the masses, okay, M1 and 2. But which value? That's a crucial point. So in order to get this strong agreement between the measured value and those predicted by the quark model, one has to use these rather large values. So M up and down order of 0.3 GeV, and M strange order of 0.4 GeV. And then this is the experimental value extracted from experimental fit, okay, from the A parameter. So what is the meaning of these large masses? So these quark masses are indeed very different from the bare quark masses that we know that are of the order of few MeV. So 2 MeV or 4 MeV for the down and something like 96 for the strange quark. So there is a huge difference. Okay. Now these bare masses are also known as the current masses, whereas these dressed masses are known as the constituent masses, which are much larger. And the physical meaning is that these constituent masses actually corresponds to quarks which are dressed by the cloud of gluons and the virtual quark-antiquark pair originating from the QCD interaction. So in other words, this simple quark model does not include any QCD. Okay, the QCD was developed later on and in a completely different context. Okay, the only place where some QCD hypothesis is put is that instead of using the bare masses of the quark, one should use this dressed. Okay, where one imagine that the quark inside the baryon or the meson is surrounded by the QCD vacuum energy, so gluons and gluons that split into quark and quark. Okay, so it's like they are dressed. Okay. Now there is an important consequence of this, because the distinction between the current and the constituent masses implies that only 1% of the mass of the proton is attributable to the real mass of the quark. So if you just sum up twice the up quark mass and the down quark, you obtain something like in the order of 10 MeV, right? Whereas the mass of the proton is order of 1000 MeV, okay? So you only account for 1% of the mass of the proton if you only consider the current masses, okay? And the current masses, as we will study at the end of the course, are those that quarks achieve by interacting with the Higgs field, so through the Higgs mechanism. So in other words, the 99% of the masses of the proton, and so the mass of matter that surround us, okay, does not come from the Higgs mechanism, but instead from the internal QCD gluon field, or from the internal energy of QCD. Okay, so the Higgs mechanism that we will study is a fundamental mechanism that allows to provide masses to bosons and also to elementary particles like fermions and quarks, but it only accounts for 1% of the mass that we observe in our ordinary world. All the rest come from the QCD energy. Now, just to conclude in a moment, this will take really 2 minutes. Let me go to some of these examples to calculate the mass of these mesons. I'll give you a couple of examples and then you can do the other as homework. Okay. So this is the problem. I think it was 5.8. So calculate the mass of the following mesons using the phenomenological formula. Okay. So let's start from the charged pions. Okay. So we know that the pi plus is a u d bar, the pi minus is a u bar d object, and they come in a JP0 minus quantum state. So these are pseudoscalar mesons. So we have to use the formula for the pseudoscalar meson, that is mu plus md minus 3a divided by 4 times mu md. Okay. Now we assume that the mass of the u quark is equal to the mass of the down quark, the constituent masses. Okay. So this is almost equal to twice mu minus 3a 4 times mu squared. Okay. And from the text, we know that the value to be used for A is 0.06 GeV to the cube. So let's just substitute here. So we have twice the invariant mass. The constituent masses are also provided by the text. So I didn't put them, but the mass of U is 0.307 GeV, and it is the same as for the down quark. So it is twice 0.307 GeV minus 3 times 0.06 GeV to the cube divided by 4 times the mass of the U quark, the constituent mass of the U quark. And so at the end, it is 0.136 GeV, okay? To be compared with the experimental value, that is 139.6 GeV. So a rather good agreement. We can skip, okay, let's take the kaons, okay? Now the K plus is equal to U S bar, the K minus to U bar S. They are still pseudoscalar mesons. So the mass of the K mesons is the mass of the U plus the mass of the strange quark minus 3 times A for the mass of the U times the mass of the strange quark. For the strange quark, we have to use from the text 0.490 GeV. So we just substitute here. So it's 0.307 GeV plus 0.490 GeV minus 3 times 0.06 GeV to the cube divided 4 times 0.307 GeV times 0.490 GeV, and the result is 0.498 GeV to be compared with the experimental value of 0.494 GeV. Okay, so again, excellent agreement. Let me just give you the very last example for a vector meson. Let's take, for instance, okay, the last one. So G. This is the phi in the phi. So the mass of the phi, which is an S bar mesons, as we know. So this is now instead a vector meson. So JP1 minus. So the mass of the phi meson is the mass of the strange quark plus the mass of the strange quark. Now we have to use the other formula, the one for vector meson. So this is A divided 4 times the mass of the strange quark squared, and we have a plus sign here in this case. So this is twice 0.490 GeV plus 0.06 GeV to the cube divided by 4 times 0.490 GeV squared, and the result is 1.032 GeV to be compared with the experimental value, that is 1.019 GeV approximately. So again, a very good agreement. All the other you can do as a homework. Okay, grazie per la pazienza. Thanks for prolonging this lesson, but at least we are done with the mesons, and next time we will continue with the baryons. Any questions?
No question, thank you.
Ok, allora buon pranzo a tutti, buon weekend, ci si vede mercoledì, no, quando ci si vede? Non ricordo più. No, il prossimo, sì, sì, ci si vede il mercoledì prossimo.
Sì.
Okay.
Buon pranzo, arrivederci.
Arrivederci.
Buon pranzo, arrivederci, prof.
Arrivederci.